In the beginning, there was darkness. Not the absence of light we know on Earth, but a profound cosmic darkness that stretched across billions of light years, punctuated only by the faint glow of distant galaxies. For centuries, astronomers believed these galaxies were scattered randomly across the cosmos, like stars thrown carelessly across a velvet canvas. But as our telescopes grew more powerful and our surveys more ambitious, we began to see something extraordinary, a pattern emerging from the void, a structure so vast and intricate that it defies human comprehension. This is the story of the cosmic web, the largest known structure in the universe, a delicate lattice of matter that connects every galaxy, every star, every atom in existence. Imagine, if you will, standing in a vast cathedral, but instead of stone pillars and arched ceilings, you're surrounded by rivers of galaxies flowing along invisible threads that stretch across hundreds of millions of light years. These threads, called filaments, are the highways of the cosmos, along which matter has traveled for over 13 billion years. The cosmic web was first glimpsed in the 1980s, when astronomers conducted the CFA redshift survey at the Harvard-Smithsonian Center for Astrophysics. They measured the distances to thousands of galaxies, plotting their positions in three-dimensional space. What emerged from their data was startling. Galaxies weren't uniformly distributed at all. Instead, they clustered along thin filaments and sheets, surrounding enormous voids, regions of space nearly empty of galaxies, stretching across hundreds of millions of light years. Picture a vast ocean of darkness, and within it, soap bubbles of emptiness. The galaxies gather at the intersections where these bubbles meet, forming delicate membranes and threads. The largest of these voids, like the Boötes void, discovered in 1981, spans approximately 330 million light-years across. To put this in perspective, our own Milky Way galaxy is just 100,000 light-years in diameter. The Boötes void is so large that it contains only about 60 galaxies, where we might expect to find thousands based on the average density of the universe. The cosmic web consists of four main components, each playing a crucial role in the universe's architecture. First, there are the filaments, long, thread-like structures of dark matter and galaxies that form the web's primary framework. These filaments can stretch for hundreds of millions of light-years, containing chains of galaxy clusters and groups. Then there are the nodes, or clusters, where multiple filaments intersect. These are the universe's great cities, containing hundreds or even thousands of galaxies bound together by gravity. Between the filaments lie the walls or sheets, flattened structures where galaxies spread out in two-dimensional patterns. And finally, there are the voids, the empty spaces that make up most of the universe's volume. These voids aren't completely empty. They contain some dim galaxies and vast quantities of dark matter and dark energy, but they're remarkably underdense compared to the filaments and clusters. The cosmic web's existence tells us something profound about the universe's history. In the moments after the Big Bang, about 13.8 billion years ago, the universe was remarkably smooth and uniform. Tiny quantum fluctuations in density, differences of just 1 part in 100,000, were all that distinguished one region of space from another. But these minuscule variations were the seeds from which the entire cosmic web would grow. As the universe expanded and cooled, these tiny, overdense regions began to attract more matter through gravity. Dark matter, which makes up about 85% of all matter in the universe, played the crucial role. Because dark matter doesn't interact with light or normal matter except through gravity, it began collapsing into structures earlier than ordinary matter could. These dark matter halos became the gravitational wells into which ordinary matter, hydrogen and helium gas, would eventually fall, lighting up as the first stars and galaxies. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in astronomical history, has given us our clearest view of the cosmic web. Beginning in 2000, this survey has mapped the positions and distances of millions of galaxies, creating a three-dimensional atlas of the nearby universe. When you look at these maps, the web-like structure is unmistakable. Galaxies trace out a cosmic neural network, resembling nothing so much as the neurons in a human brain or the mycelium of fungi spreading through forest soil. This resemblance isn't just poetic. It reflects a deep truth about how structures form in complex systems. Whether we're looking at the universe at its largest scales, the neural networks in our brains, or the distribution of cities connected by highways, similar patterns emerge. These patterns are the result of matter organizing itself under the influence of fundamental forces, seeking equilibrium in an ever-expanding universe. Let us journey now along one of these cosmic filaments, these magnificent highways that channel matter across the universe. Close your eyes and imagine yourself drifting through intergalactic space, leaving behind the familiar spiral arms of our Milky Way. As you travel outward, millions of light years pass beneath you, and gradually, the broader structure of the cosmos reveals itself. The filament you're traveling along is called the Pisces-Cetus Supercluster complex, one of the largest known structures in the observable universe. It stretches for roughly 1 billion light years, a distance so vast that light itself, traveling at 186,000 miles per second, takes 1 billion years to traverse it. This single structure contains hundreds of thousands of galaxies, each containing hundreds of billions of stars, and countless planets orbiting those stars. Filaments are not uniform rivers of galaxies. As you drift along this cosmic highway, you notice that galaxies cluster more densely in some regions than others, like traffic building up along a highway. These denser regions are galaxy clusters, gravitational meeting points where hundreds or thousands of galaxies swarm together. The Virgo cluster, located about 65 million light years from Earth, is one such gathering point in our cosmic neighborhood, containing over 1,500 galaxies bound together by their mutual gravitational attraction. The matter in these filaments isn't just galaxies and stars. It's primarily dark matter, that mysterious substance that makes up most of the universe's mass but doesn't emit, absorb, or reflect light. We know it's there because we can see its gravitational effects on visible matter. Galaxies and clusters move faster than they should if only visible matter were present. The dark matter in filaments forms the invisible scaffolding along which ordinary matter flows. Between the galaxies, the filaments contain vast quantities of gas, primarily hydrogen and helium left over from the Big Bang. This intergalactic medium is incredibly thin by Earth standards, with densities far lower than the best vacuum we can create in laboratories. Yet because the volumes involved are so enormous, these filaments contain more ordinary matter than all the stars and all the galaxies combined. For many years, this gas was purely theoretical. We knew it had to be there based on our understanding of Big Bang nucleosynthesis, the process that created the first atomic nuclei, but we couldn't see it. The gas is too hot to form stars, but too cool to emit X-rays easily. It exists in a temperature range between 100,000 and 10 million Kelvin, making it incredibly difficult to detect. Then, in 2019, 2 independent teams of astronomers finally confirmed its existence. They used pairs of bright quasars, extremely luminous galactic cores powered by supermassive black holes, as cosmic flashlights. The light from these quasars passes through the filaments on its way to Earth, and the gas in the filaments leaves a subtle fingerprint in the quasar light spectrum. By comparing the light from 2 quasars lying near each other in the sky, astronomers could isolate the signature of the filament gas, finally revealing these ghostly rivers of matter. The discovery confirmed what simulations had long predicted. Filaments contain about 50% of all the ordinary matter in the universe. This solved a long-standing mystery called the missing baryon problem. Baryons are ordinary matter particles, protons and neutrons, and based on observations of the cosmic microwave background radiation, scientists knew how many baryons the Big Bang should have created. But when they added up all the baryons they could see in stars, galaxies, and gas clouds, they came up short. About half the baryons were missing. They were hiding all along in the warm gas of the cosmic web's filaments. Traveling along our filament, you would witness galaxies in various stages of evolution. Some are young, blue, and actively forming stars from the gas they've drawn from the filament. Others are older, redder, having exhausted their star-forming fuel. The filaments act as feeding tubes, channeling fresh gas into galaxies and allowing them to continue creating new generations of stars. The flow of matter along filaments isn't random. Simulations show that galaxies actually move along these cosmic highways, slowly drifting toward the nodes where filaments intersect. This journey can take billions of years, and along the way, galaxies may merge with others, growing larger and more massive. Our own Milky Way is on such a journey, slowly moving through the local sheet, a flattened wall-like structure, toward the Virgo cluster. The temperature of gas and filaments varies depending on location. Near the outskirts, where the filament borders on void regions, the gas may be cooler, around 100,000 Kelvin. Deeper within the filament, and especially near galaxy clusters, the gas can heat up to millions of degrees as it falls into the gravitational wells created by dark matter halos. This heating occurs through a process called gravitational shock heating. As gas falls into denser regions, it compresses and heats up, similar to how a bicycle pump gets warm when you compress air. The filaments themselves are not static structures. They evolve over cosmic time, growing denser and more defined as matter continues to flow along them. In the early universe, just a few 100 million years after the Big Bang, the cosmic web was much more subtle, with filaments barely distinguishable from the surrounding space. As billions of years passed and gravity continued its patient work, the web became more pronounced, the filaments grew thicker, and the voids became emptier. Now, let us turn our attention to the spaces between, the cosmic voids that occupy most of the universe's volume. Imagine leaving the bright filament behind and drifting into one of these vast, empty regions. The galaxies grow sparse, their light dimming as you move away from the web's bright threads. Soon, you're floating in a darkness broken only by the occasional faint glow of isolated dwarf galaxies. The Boötes void, discovered by Robert Kirshner and colleagues in 1981, was one of the first great voids to be recognized. Spanning approximately 330 million light-years, this region contains only about 60 galaxies, a fraction of what its volume should hold based on the average density of the universe. If you were somehow standing on a planet orbiting a star in a galaxy within the Boötes void, your night sky would be profoundly empty. Where we on Earth can see thousands of galaxies with powerful telescopes, you might see only a handful. Voids are the universe's quiet chambers, vast bubble-like regions where matter is sparse and the normal activity of galaxy formation has been suppressed. They form naturally as the cosmic web evolves. As matter flows along filaments toward nodes and clusters, it evacuates these regions, leaving them increasingly empty. It's a cosmic sorting process, with gravity acting as the sorter, concentrating matter in some places while leaving others nearly barren. But empty is relative. Voids aren't complete vacuums. They contain dark matter, though in lower concentrations than the filaments. They also contain dark energy, that mysterious force causing the universe's expansion to accelerate. In fact, because dark energy has a nearly uniform density throughout space while matter clumps in filaments, the voids are dominated by dark energy's influence more than any other region of the universe. The few galaxies that do exist within voids are peculiar creatures. They tend to be smaller, bluer, and more actively forming stars than galaxies in denser environments. This seems counterintuitive. You might expect galaxies in sparse regions to be starved of the gas needed for star formation. But the opposite is true. Void galaxies are isolated, free from the gravitational harassment that galaxies in clusters experience. They haven't had their gas stripped away by interactions with other galaxies or with hot intracluster gas. One of the largest voids known is the Giant Void, also called the Giant Void in Cain's Venatici, which stretches approximately 1.3 billion light-years across. To cross it at the speed of light would take longer than Earth has existed. These immense empty regions aren't just cosmic curiosities. They're crucial laboratories for understanding dark energy and the universe's expansion. Astronomers study voids by looking at how they grow over time. In a universe dominated only by matter, voids would expand more slowly as the universe's expansion gradually decelerates under gravity's pull. But observations show that voids are expanding faster than this prediction, their boundaries pushing outward at an accelerating rate. This acceleration is one of the key pieces of evidence for dark energy's existence. The shapes of voids are also revealing. They're not perfect spheres, but rather irregular, roughly spherical regions that fit together like bubbles and foam. This bubble-like structure is exactly what we'd expect from simulations of cosmic structure formation. As matter collapsed into filaments and sheets under gravity's influence, it left behind these bubble-like voids, creating a cosmic foam structure. Within the voids, the intergalactic medium is even thinner than in filaments. The gas density drops to just a few atoms per cubic meter, far more tenuous than the space between stars in our galaxy. This gas is also cooler than in filaments, maintaining temperatures around 100,000 Kelvin or less. Without the continuous flow of matter and the compression that occurs in denser regions, void gas remains in this relatively cool state. The boundaries of voids, the regions where they meet filaments, are particularly interesting. These are transition zones where the density gradually increases as you move from void to filament. Astronomers have found that galaxies at void boundaries show different properties than those in void centers or in filaments. They're in the process of being influenced by the web, beginning to channel their gas along gravitational gradients toward the filaments. Some voids show evidence of internal structure, smaller filaments, and mini-walls within the larger void. These structures form from the subtle density variations that existed even in underdense regions. While the overall void is empty compared to the cosmic average, within it, matter still tries to organize itself according to the same gravitational principles that shaped the larger cosmic web. The discovery and mapping of voids have revolutionized our understanding of a universe's large-scale structure. The 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey have mapped thousands of voids, revealing that they occupy about 70 to 80% of the universe's volume, while containing only about 10% of its galaxies. This inverted distribution, most of the volume being nearly empty while most of the galaxies crowd into a small fraction of space, is one of the cosmic web's most striking features. Let us now journey to the nodes of the cosmic web, the galaxy clusters where multiple filaments converge. These are the universe's great cities, gravitational crossroads where hundreds or thousands of galaxies gather, bound together by the immense mass of dark matter halos that anchor the web structure. The Coma Cluster, located about 320 million light-years from Earth, is a magnificent example. It contains over 1,000 identified galaxies, most of them elliptical galaxies that have long since exhausted their star-forming gas. The cluster's total mass is approximately 10 quadrillion times that of our Sun, a number so large it defies intuition. Most of this mass is dark matter, which reveals itself through its gravitational effects on the cluster's galaxies and the hot gas between them. This gas, called the intracluster medium, is one of the most fascinating components of galaxy clusters. Heated to temperatures between 10 million and 100 million Kelvin by the cluster's immense gravity, it emits X-rays that space telescopes like NASA's Chandra X-ray Observatory can detect. When astronomers image clusters in X-ray light, they see vast, diffuse clouds of gas extending far beyond the visible galaxies, sometimes spanning millions of light years. The intracluster medium contains more ordinary matter than all the stars in all the cluster's galaxies combined. This gas was once inside galaxies, but was stripped out through several processes. As galaxies move through the cluster at high speeds, sometimes thousands of kilometers per second, they experience ram pressure stripping, where the intracluster medium acts like a wind, blowing gas out of the galaxy. Galaxies also interact gravitationally with each other, and these tidal interactions can pull gas out into the space between galaxies. The Virgo cluster, our nearest rich galaxy cluster at about 65 million light-years away, is slowly pulling our local group of galaxies toward it. Our Milky Way, along with the Andromeda Galaxy and dozens of smaller galaxies, is falling toward Virgo at approximately 250 kilometers per second. This journey will take many billions of years, and long before we reach Virgo, our Milky Way will have merged with Andromeda, creating a larger elliptical galaxy. Beyond individual clusters lie superclusters, collections of multiple clusters and groups linked by the cosmic web's filaments. The Laniakea Supercluster, whose name means immense heaven in Hawaiian, was mapped in 2014 by Brent Tully and his colleagues. Using a new technique that tracks the motions of galaxies rather than just their positions, they discovered that our Milky Way is part of this structure, which spans 520 million light-years and contains approximately 100,000 galaxies. Laniakea's center is the Great Attractor, a massive gravitational anomaly in the direction of the constellations Triangulum Australe and Norma. First detected in the 1970s, the Great Attractor influences the motion of galaxies across hundreds of millions of light-years. Our local group, the Virgo cluster, and many other structures are all flowing toward it at speeds of several hundred kilometers per second. The Great Attractor itself appears to be a particularly dense section of the cosmic web where multiple filaments converge. The largest known structures in the universe are supercluster complexes, chains of superclusters linked along particularly long filaments. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches approximately 10 billion light-years across. At this scale, we're approaching the limits of structure formation in the universe. Structures much larger than this shouldn't exist according to our current understanding of cosmology, because the universe hasn't been around long enough for gravity to organize matter at such enormous scales. Within clusters, galaxies lead violent lives. They collide and merge far more frequently than in less dense environments. When two galaxies collide, their stars rarely strike each other. Space between stars is so vast that even during a galactic collision, stellar collisions are extraordinarily rare. But the gas clouds in the galaxies do collide, compressing and triggering intense bursts of star formation. These starburst galaxies can form stars hundreds of times faster than normal spiral galaxies like our Milky Way. The galaxies in cluster centers tend to be elliptical, smooth, featureless collections of stars lacking the spiral arms and active star formation seen in disk galaxies. This is no coincidence. The cluster environment transforms galaxies. The stripping of gas halts star formation. Repeated galaxy mergers destroy spiral structures, scrambling stellar orbits and creating the smooth, elliptical shapes. After billions of years in a cluster environment, even a beautiful spiral galaxy like our Milky Way would be transformed into a red, dead elliptical galaxy. At the very centers of massive clusters often lurks a brightest cluster galaxy, an enormous elliptical galaxy that has grown by cannibalizing its neighbors. These galaxies can contain trillions of stars and span hundreds of thousands of light years. The brightest cluster galaxy in the Coma Cluster, NGC 4889, contains a supermassive black hole estimated at 21 billion times the mass of our Sun, one of the largest black holes ever discovered. Beneath all that we can see, the glowing galaxies, the hot gas, the stars and planets, lies an invisible architecture that makes it all possible. This is the realm of dark matter, the mysterious substance that outweighs ordinary matter 5 to 1 and provides the gravitational framework for the cosmic web's existence. Dark matter was first inferred in the 1930s by Swiss astronomer Fritz Zwicky, who studied the Coma Cluster. He calculated the cluster's mass two different ways. First, by adding up the mass of all visible galaxies, and second, by measuring how fast galaxies were moving within the cluster. The second method gave a result hundreds of times larger than the first. The galaxies were moving so fast that, if only visible matter were present, the cluster should have flown apart long ago. Something invisible was providing additional gravity to hold it together. In the 1970s, Vera Rubin and Kent Ford made similar observations of individual galaxies. They measured how fast stars orbit at different distances from galactic centers. According to Newton's laws, stars farther from the center should orbit more slowly, just as Neptune orbits the Sun more slowly than Earth does. But Rubin and Ford found that stars far from galactic centers were orbiting just as fast as stars closer in. This flat rotation curve implied that galaxies were surrounded by vast halos of invisible matter extending far beyond the visible galaxy. Today, we have multiple lines of evidence for dark matter's existence. One of the most compelling comes from gravitational lensing. Einstein's theory of general relativity predicts that mass curves space-time, and light follows these curves. When light from distant galaxies passes by a massive object like a galaxy cluster, the cluster's gravity bends the light, distorting the appearance of the background galaxies into arcs and multiple images. By carefully mapping these distortions, astronomers can create maps of where mass is located in the cluster, regardless of whether that mass emits light. These maps consistently show that most mass is dark matter, distributed in a roughly spherical halo around the cluster's visible components. The Hubble Space Telescope has captured stunning images of this gravitational lensing, revealing the invisible dark matter structure through its effect on light. The bullet cluster, formed by the collision of two galaxy clusters, provides perhaps the most direct evidence for dark matter. Observed in 2006, this system shows a clear separation between the hot X-ray emitting gas, ordinary matter, and the majority of the mass, dark matter. When the clusters collided, the gas clouds interacted and were slowed down, remaining near the collision center. But the dark matter, which doesn't interact with ordinary matter or itself except through gravity, passed straight through. Gravitational lensing maps show that most of the mass is now separated from most of the ordinary matter, direct proof that dark matter exists as a separate substance. Computer simulations of cosmic structure formation rely heavily on dark matter. When scientists simulate the universe's evolution, starting from the tiny density fluctuations present shortly after the Big Bang, they must include dark matter to reproduce the structures we observe today. Simulations with only ordinary matter fail to form the cosmic web we see. The dark matter collapses first, creating gravitational wells into which ordinary matter falls, allowing galaxies to form earlier and faster than they otherwise could. These simulations reveal dark matter's structure in exquisite detail. Each filament of the cosmic web is really a filament of dark matter, containing smaller subfilaments and clumps. At every scale, from individual galaxies to superclusters, dark matter halos provide the gravitational container that holds ordinary matter. The Millennium simulation, run in 2005, followed the evolution of over 10 billion dark matter particles from the early universe to the present day, creating a detailed map of dark matter's cosmic distribution. What is dark matter made of? Despite decades of searching, we still don't know. It cannot be ordinary matter made of protons, neutrons, and electrons, because such matter would have left clear signatures in the cosmic microwave background radiation and in Big Bang nucleosynthesis. It must be something else, perhaps an exotic particle that has barely interacted with ordinary matter since the Big Bang. Leading candidates include WIMPs, weakly interacting massive particles, hypothetical particles that interact via gravity and the weak nuclear force but not electromagnetism, experiments deep underground, shielded from cosmic ray interference, are searching for the rare occasions when a dark matter particle might scatter off an atomic nucleus. So far, these searches have returned null results, but they're becoming more sensitive with each passing year. Another possibility is axions, extremely light particles originally proposed to solve problems in particle physics. If dark matter is made of axions, there would be trillions upon trillions passing through every cubic centimeter of space, including your body, every second. Special experiments using powerful magnetic fields and supercool detectors are searching for the faint signals these particles might produce. The cosmic web's dark matter structure determines where galaxies form and how they evolve. Galaxies only form in dark matter halos above a certain mass threshold. Smaller halos don't have enough gravity to hold onto the gas needed for star formation. Our Milky Way resides in a dark matter halo estimated to contain about 1 trillion solar masses, extending perhaps 600,000 light-years from the galactic center, 6 times the visible galaxy's diameter. To truly understand the cosmic web's origin, we must journey backward in time to an epoch when the universe was young, hot, and remarkably uniform. This is the era of the cosmic microwave background, the oldest light in the universe, released 380,000 years after the Big Bang, when the cosmos was just 1/1100th its current size. Before this moment, the universe was opaque. It was filled with a hot plasma of electrons and atomic nuclei, and any photon traveling through this plasma would quickly scatter off a free electron, unable to travel far. The universe was luminous but invisible, like being inside a thick fog illuminated by bright lights. As the universe expanded and cooled, it eventually reached a temperature of about 3,000 Kelvin, cool enough for electrons to combine with nuclei to form neutral atoms. This process, called recombination, made the universe transparent for the first time. Photons could suddenly travel freely across space, no longer scattering off free electrons. The light released at this moment has been traveling through space ever since, stretched by the universe's expansion from visible and infrared wavelengths to microwaves. This is the cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964. The cosmic microwave background appears remarkably uniform, with a temperature of 2.725 Kelvin in every direction. But when we measure precisely, we find tiny temperature fluctuations, differences of about 1 part in 100,000. These fluctuations are the seeds from which all cosmic structure grew. Regions that were slightly denser than average appear slightly warmer in the cosmic microwave background, while less dense regions appear slightly cooler. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, and the European Space Agency's Planck satellite, launched in 2009, created detailed maps of these temperature fluctuations. These maps are among the most important scientific images ever captured. They show us the universe as it was in its infancy, before stars or galaxies existed, when the seeds of the cosmic web were just tiny quantum fluctuations in density. The pattern of fluctuations in the cosmic microwave background tells us about the composition and geometry of the universe. By analyzing the sizes and amplitudes of temperature variations, cosmologists can determine how much ordinary matter, and dark energy the universe contains. These measurements agree remarkably well with other independent observations, giving us confidence in our cosmic model. The fluctuations follow a specific pattern predicted by cosmological theory. The largest fluctuations correspond to regions that would become superclusters and voids. Medium-sized fluctuations would become galaxy clusters. Smaller fluctuations would eventually collapse into individual galaxies. The cosmic microwave background provides a blueprint for all the structure we see in the universe today. Sound waves in the early universe created some of these patterns. Before recombination, pressure from radiation created acoustic oscillations, sound waves traveling through the plasma at about half the speed of light. These waves couldn't travel far before the universe became transparent and the oscillations froze in place. The distances they traveled appear as characteristic scales in the cosmic microwave background's temperature pattern, and these same scales appear in the distribution of galaxies billions of years later. The cosmic microwave background also reveals the universe's geometry. If the universe had positive curvature, like the surface of a sphere, the pattern of fluctuations would appear magnified. If it had negative curvature, like a saddle, the pattern would appear demagnified. Observations show that the universe is remarkably flat. The cosmic microwave background pattern appears exactly as it should in a flat universe, where parallel lines remain parallel forever. Dark matter's presence is written into the cosmic microwave background. The relative heights of different peaks in the fluctuation pattern depend on the ratio of dark matter to ordinary matter. Too little dark matter, and the peaks would have different heights than observed. Too much, and they'd be different still. The measurements point to a universe where dark matter outweighs ordinary matter by about 5 to 1. From these tiny fluctuations, differences of 1 part in 100,000 grew the vast cosmic web we see today. Gravity amplified the density contrasts over billions of years. The slightly denser regions attracted more matter, becoming denser still, while slightly less dense regions lost matter to their neighbors, becoming voids. This process continued for billions of years, creating the filaments, clusters, and voids that define the universe's large-scale structure. Computer simulations start from cosmic microwave background fluctuations and evolve them forward using the laws of gravity and hydrodynamics. These simulations successfully reproduce the cosmic web's statistical properties, the distribution of void sizes, filament lengths, cluster masses. This agreement between prediction and observation is one of modern cosmology's great triumphs, confirming our understanding of how cosmic structure forms. Now let us venture into the cosmic dawn, that mysterious epoch between the universe's first transparency and the formation of the first stars. This was the Dark Ages, a time when the universe was filled with neutral hydrogen gas. No stars yet existed to light the void, and the cosmic web was beginning to take shape in the darkness. The first structures to form were dark matter halos, collapsing under their own gravity from the overdense regions imprinted in the cosmic microwave background. These earliest halos were small, perhaps 1 million times the mass of our Sun, and they formed when the universe was just a few 100 million years old. Into these gravitational wells, ordinary matter, hydrogen and helium gas, began to fall, heating as it compressed. When gas clouds reach sufficient density and temperature, they can collapse and fragment into the first stars. These population 3 stars, as astronomers call them, were very different from the Sun. They formed from pristine gas containing only hydrogen and helium, without the heavier elements created in later stellar generations. Theory predicts they were massive, perhaps 100 to 300 times the Sun's mass, and incredibly luminous, burning through their fuel in just a few million years. These first stars began the process of reionization, flooding the universe with ultraviolet radiation that stripped electrons from neutral hydrogen atoms, making the universe transparent to ultraviolet light for the first time. NASA's James Webb Space Telescope, launched in 2021, is designed to observe these earliest galaxies, detecting their faint infrared light that has been stretched by cosmic expansion from ultraviolet wavelengths. As dark matter halos grew larger through mergers and continued infall, they could host larger collections of stars, the first galaxies. These were tiny compared to modern galaxies, containing perhaps 1 million to 1 billion stars, but they were the seeds from which all subsequent galaxies grew. They formed preferentially along the cosmic web's developing filaments, where dark matter had concentrated most strongly. The early universe saw vigorous structure formation. Small halos merged into larger ones at a rapid pace. Galaxies collided and merged frequently. The cosmic web structure became more defined as matter continued flowing from voids into filaments and from filaments into clusters. The universe was a more violent, chaotic place than today, with more mergers, more intense star formation, and more supermassive black holes growing rapidly in galactic centers. By the time the universe was about 1 billion years old, the reionization process was largely complete. The universe had transformed from neutral and opaque to ionized and transparent, the state it remains in today. This reionization was driven by the combined ultraviolet radiation from billions of early galaxies and possibly from the first quasars, extremely luminous objects powered by supermassive black holes consuming gas at the centers of galaxies. Evidence for the early cosmic web comes from distant quasars. The light from these objects, emitted when the universe was just a few percent of its current age, passes through the intervening space before reaching us. Along the way, it encounters clouds of hydrogen gas, which absorb light at characteristic wavelengths. By studying these absorption features, called the Lyman alpha forest, astronomers can map the distribution of gas in the early universe. These observations reveal that even at early times, gas was distributed along filaments and collected in overdense regions. The cosmic web's basic structure was already in place when the universe was less than 2 billion years old. However, it was much less pronounced than today. The contrast between dense and empty regions has grown over cosmic time as gravity continued its patient work. The Hubble Ultra Deep Field, an image created by pointing the Hubble Space Telescope at a tiny patch of seemingly empty sky for millions of seconds, reveals thousands of galaxies at various distances and ages. The most distant galaxies in this image, appearing as small reddish smudges, existed when the universe was less than 1 billion years old. They show us the cosmic web in its youth, when structures were smaller and the universe was more uniformly filled with galaxies. Some of the earliest superclusters have been identified at great distances. These concentrations of multiple galaxies and galaxy groups existed when the universe was just 2 to 3 billion years old. Their existence tells us that structure formation proceeded rapidly in the early universe, with gravity working efficiently to gather matter from vast regions of space. The process of hierarchical structure formation, small halos merging to form larger ones, continues today, though at a slower pace. Our Milky Way is currently in the process of cannibalizing several smaller satellite galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart by our galaxy's gravity, with streams of stars from this unfortunate galaxy visible wrapping around the Milky Way. In about 4 billion years, we'll merge with our large neighbor, the Andromeda Galaxy, in a dramatic collision that will transform both galaxies. How do astronomers map something as vast and ethereal as the cosmic web? The challenge is immense. The web spans billions of light years, contains structures both visible and invisible, and exists in a four-dimensional space-time that we can only observe from one location. Yet through clever techniques and massive surveys, astronomers have created increasingly detailed maps of the universe's architecture. The fundamental tool is redshift measurement. As the universe expands, light from distant galaxies is stretched to longer wavelengths, shifting toward the red end of the spectrum. The amount of redshift tells us how fast a galaxy is receding, which in turn tells us its distance. By measuring redshifts for millions of galaxies, astronomers can create three-dimensional maps showing where galaxies are located in space. The Sloan Digital Skies Survey has been the workhorse of cosmic web mapping for over 2 decades. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, the survey has measured redshifts for over 4 million galaxies and quasars. The resulting maps reveal the cosmic web in unprecedented detail, showing filaments, clusters, and voids across billions of light years. Each night of observing follows a precise pattern. The telescope points at a predetermined patch of sky, and light from up to 1,000 galaxies simultaneously passes through optical fibers to spectrographs that spread the light into its component wavelengths. By identifying characteristic spectral features and measuring how much they've shifted toward the red, astronomers determine each galaxy's redshift and distance. The accumulating data creates maps that look like slices of cosmic web, with each slice representing a range of distances. When you stack these slices together, the three-dimensional structure emerges. Galaxies trace out filaments that appear to flow like rivers. Clusters mark the nodes where filaments meet. Voids appear as vast, empty bubbles. The overall impression is of a complex, interconnected network spanning the observable universe. Other surveys have complemented the Sloan work. The 2DF Galaxy Redshift Survey, conducted using the Anglo-Australian telescope, mapped over 220,000 galaxies. The VIMO's Public Extragalactic Redshift Survey used the Very Large Telescope in Chile to map distant galaxies, revealing the cosmic web as it appeared billions of years ago. Each survey adds detail to our understanding of how the web has evolved over cosmic time. Mapping dark matter requires different techniques. One powerful method uses weak gravitational lensing. As light from distant galaxies travels through the universe, its path is subtly bent by the gravity of intervening matter, including dark matter. This bending causes tiny distortions in the shapes of background galaxies. By measuring how millions of galaxies appear slightly stretched or squeezed, astronomers can map where dark matter is concentrated. The Dark Energy Survey, conducted using a camera on the Blanco telescope in Chile, has used this technique to map dark matter across a large fraction of the southern sky. The resulting maps show dark matter filaments connecting galaxy clusters, confirming that visible galaxies trace the underlying dark matter structure. The agreement between galaxy positions and dark matter concentrations validates our picture of how structure forms. X-ray telescopes provide another window on the cosmic web. The Chandra X-ray Observatory and Newton satellite have detected X-rays from the hot gas in galaxy clusters and the filaments connecting them. These observations reveal the warm-hot intergalactic medium, gas at temperatures between 100,000 and 10 million degrees Kelvin that contains much of the universe's ordinary matter. Radio observations contribute by detecting neutral hydrogen gas through its emission at a wavelength of 21 centimeters. Future radio surveys, using telescopes like the Square Kilometer Array currently under construction, will map hydrogen throughout the cosmic web, revealing the distribution of gas that hasn't yet formed into stars. This will provide a census of the universe's fuel for future star formation. The combination of all these techniques, optical redshift surveys, dark matter mapping through gravitational lensing, X-ray observations of hot gas, radio observations of neutral hydrogen, creates a multi-wavelength picture of the cosmic web. Each wavelength reveals a different component. Galaxies show where stars have formed, X-rays show hot gas, dark matter maps show the gravitational scaffolding, Radio observations show neutral gas. Computer simulations play a crucial role in interpreting observations. Modern simulations like the Illustrious Project and Eagle, evolution and assembly of galaxies and their environments. Simulation combine gravity, gas dynamics, star formation, black hole growth, and feedback from stars and black holes. These simulations create virtual universes that can be compared directly with observations, testing our understanding of the physical processes that shape the cosmic web. The cosmic web is not a static structure frozen in time, but a living, evolving entity that has changed dramatically over the universe's 13.8 billion year history. To understand this evolution, we must think in cosmic timescales, watching as filaments thicken, clusters grow, and voids expand across billions of years. In the early universe, shortly after recombination, the web was barely perceptible. The density contrasts were tiny, just those 1 part in 100,000 fluctuations visible in the cosmic microwave background. Dark matter began collapsing first, creating shallow gravitational wells. Ordinary matter, still pressure-supported by radiation, resisted collapse until the universe had cooled sufficiently. By the time the first stars formed, perhaps 200 million years after the Big Bang, the web had become more defined. Small dark matter halos, each containing a few million times the sun's mass, had collapsed and were beginning to merge. These halos marked the densest regions, the seeds of future filaments. The space between these seeds was beginning to empty as matter drained into the developing structures. The epoch of galaxy formation, from about 500 million to 3 billion years after the Big Bang, saw rapid web evolution. Halos merged hierarchically, with small halos combining into larger ones. The first galaxies formed in these merging halos, lighting up along the web's filaments like lights turning on along a highway system. Star formation rates were higher than today, fueled by the abundant gas flowing along filaments. During this era, the cosmic web guided galaxy formation. Galaxies formed preferentially in filaments because that's where dark matter and gas concentrated. The filaments acted as assembly lines, with smaller galaxies merging as they moved along the filaments toward nodes. The largest galaxies formed at the nodes, where multiple filaments converged and merger rates were highest. As the universe aged, the web continued evolving, but at a slower pace. The filaments grew thicker and more pronounced as they attracted more matter from their surroundings. Voids expanded, pushing matter toward the boundaries where filaments formed. The universe underwent a gradual phase transition from a relatively uniform distribution with subtle structure to the sharply defined web we see today. Galaxy clusters, the web's nodes, grew through mergers and continued infall. When two clusters merge, the event is one of the universe's most energetic phenomena since the Big Bang. The dark matter halos pass through each other relatively unaffected, but the hot gas clouds collide, creating shock waves that heat the gas to hundreds of millions of degrees. These cluster mergers continue shaping the web structure today. The bullet cluster collision mentioned earlier occurred relatively recently, about 150 million years ago. We observe it in the aftermath of the collision, with the gas clouds compressed and heated near the collision point, while the dark matter halos have passed through each other and now lie ahead of the gas. Such collisions have occurred throughout cosmic history, marking the growth of structure through mergers. About 6 billion years ago, a significant change occurred in the universe's evolution. Dark energy, which had always been present but was less important when the universe was denser, began to dominate the universe's dynamics. The universe's expansion, which had been slowly decelerating under the pull of matter's gravity, began to accelerate. This acceleration affects the cosmic web's evolution. Under dark energy's influence, the voids began expanding more rapidly. The accelerated expansion fights against gravity's tendency to pull matter together, slowing the growth of structure. If dark energy continues dominating, the cosmic web's evolution will eventually freeze. Filaments will stop thickening, clusters will stop growing, and the web will become a static pattern stamped on an accelerating universe. The future of the cosmic web depends on dark energy's nature. If it remains constant, a true cosmological constant as Einstein originally proposed, the web will gradually fade as expansion carries galaxy groups farther apart. In the distant future, observers in galaxies within our local group will see an increasingly empty universe as other galaxy groups recede beyond our cosmic horizon, their light redshifted to undetectability. Tracing the web's past evolution requires observing distant galaxies. Because light takes time to travel, looking at distant galaxies means seeing them as they were in the past. Observations of galaxies at various distances create snapshots of the web at different cosmic ages. These observations show that filaments were less defined in the past, clusters contained fewer galaxies, and the overall web structure was more subtle. The James Webb Space Telescope is revealing the web at unprecedented early times. Its infrared vision can detect galaxies formed when the universe was just a few 100 million years old. These observations show proto-clusters, concentrations of galaxies that will eventually become massive clusters, already in place in the young universe, confirming that structure formation began early. Computer simulations have been crucial for understanding the web's evolution. The Millennium Simulation, which tracked 10 billion dark matter particles from the early universe to the present, showed how small-scale structure gradually merged into larger structures. The simulation successfully reproduces the statistical properties of the observed cosmic web, validating our theoretical understanding. More recent simulations include the physics of gas, star formation, supernova explosions, and black hole growth. These processes provide feedback, energy that can heat gas and blow it out of galaxies, affecting future star formation. Including feedback makes simulations more realistic, better matching the properties of observed galaxies. These simulations are our laboratories for understanding how the cosmic web and the galaxies within it co-evolve. As our journey through the cosmic web draws to a close, let us return home and contemplate our place within this vast architecture. Our Earth, our Sun, our Milky Way galaxy. Each occupies a specific location within the web's hierarchy, connected through gravity and cosmic history to structures spanning billions of light years. Our Sun resides in one of the Milky Way's spiral arms, about 26,000 light years from the galactic center. The Milky Way itself is a large spiral galaxy containing perhaps 400 billion stars and at least as many planets. We orbit the galactic center once every 230 million years. Our last orbit was completed when dinosaurs first walked the Earth. The Milky Way is not alone. Along with the Andromeda Galaxy and about 54 smaller galaxies, we form the Local Group, a small galaxy group about 10 million light-years across. This group is our immediate cosmic neighborhood, bound together by gravity. The Andromeda Galaxy, our nearest large neighbor, is approaching us at about 110 kilometers per second. In approximately 4.5 billion years, our galaxies will collide and merge, transforming both into a larger elliptical galaxy that astronomers have nicknamed Milkomeda. The Local Group is a satellite structure of something much larger. We're part of the Virgo Supercluster, a concentration of galaxy groups and clusters dominated by the Virgo cluster. This supercluster spans about 110 million light-years and contains approximately 47,000 galaxies. Our Local Group lies on the supercluster's outskirts, slowly falling toward its center under gravity's pull. But even the Virgo Supercluster is just one component of something grander. In 2014, astronomers redefined our cosmic address by mapping the Laniakea supercluster, which includes Virgo and many other superclusters. Laniakea contains about 100,000 galaxies across 520 million light-years. The name, Hawaiian for immense heaven, reflects the structure's vast scale. Within Laniakea, we're located in a relatively quiet suburb. We're not in the densest regions where galaxy clusters dominate, nor in the most barren voids. Instead, we occupy a typical filament location, a region where galaxies gather in groups and small clusters, connected by the cosmic web's threads to larger structures. This location has consequences for our existence. In dense cluster environments, galaxy collisions are frequent. Gas is stripped from galaxies by hot intracluster medium, and star formation often ceases. In such environments, developing complex life might be more difficult. The intense radiation from nearby supernovae and active galactic nuclei could threaten planetary habitability. Our location in a quieter region may have been advantageous for life's development. The cosmic web extends beyond Laniakea. Our supercluster is connected to others through filaments of dark matter and galaxies. The CFA-2 Great Wall, discovered in 1989, is a sheet-like concentration of galaxies about 500 million light-years long that includes parts of Laniakea. Beyond that lie other superclusters, other filaments, all part of the universal web extending to the edges of the observable universe. The observable universe, the region from which light has had time to reach us since the Big Bang, spans about 93 billion light-years in diameter. This vast volume contains the cosmic web in all its complexity. Perhaps 2 trillion galaxies, each containing billions of stars, arranged in filaments and clusters surrounding vast voids. And beyond our observable universe, the web likely continues, perhaps infinitely, into regions forever beyond our view. Understanding our place in this structure gives us perspective. We're residents of a planet orbiting a typical star in a typical galaxy, located in a typical position within a cosmic web that fills the universe. We're made of atoms forged in stellar furnaces, scattered through space by supernova explosions, gathered by gravity into new star systems, participants in the cosmic cycle of matter. The cosmic web connects us to the universe's largest structures. The atoms in our bodies were created in massive stars that lived and died in our galaxy's disk. The iron in our blood was created in supernovae that occurred billions of years ago, perhaps in galaxies that have since merged with the Milky Way. The calcium in our bones, the oxygen we breathe, the carbon in our DNA, all were created through stellar nucleosynthesis and scattered through the galaxy to eventually gather in our solar nebula. Looking up at the night sky, we see the Milky Way's band of light, our edge-on view of our galaxy's disk. With telescopes, we can see beyond to other galaxies, to clusters and superclusters, to the filaments of the cosmic web. We're looking at the universe's architecture, the structure that has evolved over 13.8 billion years, from tiny quantum fluctuations to the magnificent web we observe today. As you drift towards sleep, imagine yourself floating through this cosmic web, through filaments stretching billions of light years, past galaxy clusters containing thousands of galaxies, into vast voids where darkness reigns. Feel yourself connected to this structure, part of the universe's grand pattern. You are made of star stuff, arranged by chance and evolution into a pattern capable of contemplating the cosmos itself. You are the universe made conscious, a way for the cosmos to know itself. The cosmic web continues its slow evolution, indifferent to our observations, yet beautiful in its complexity. Galaxies flow along filaments, clusters grow through mergers, voids expand into the darkness. And somewhere in this vast architecture, on a planet orbiting a typical star, conscious beings gaze upward and wonder at their place in the universe's grand design. Rest now, knowing you've journeyed across billions of light years, from the tiniest quantum fluctuations in the early universe to the vast filaments that fill space today. The cosmic web cradles galaxies like our Milky Way, nurturing the stars that create the elements of life. You are part of this story, this cosmic evolution, this magnificent web that connects everything that exists. Let this connection comfort you as you drift into peaceful sleep, cradled by the same forces that shape galaxies and fill the universe with light.